Okay, so we're talking about quadratic functions and models. We'll focus today on functions. On Monday, we'll mention a couple models, like, for example, revenue. Revenue in finance sometimes is a quadratic model. Model is just basically when a real-life situation can be solved using a mathematical equation, and that math equation is called a model. Okay. Let's write down some basic facts about quadratic functions. First of all, they look like this. That's their form. ax squared plus bx plus c. And just a quick note on the form, a cannot be 0. Because if a was 0, it would look like this. And that is more of a bx plus c sort of look, making it a line, right? A linear. So you're not going to ever have a equals 0, but you could certainly have b equals 0, even c equals 0. And it's still quadratic. A, B, and C are obviously numbers, right?
Yes.
Contrary to what you learned in first grade when you were told they were letters of the alphabet. Now they're numbers, we know. Okay. The domain of a quadratic function is... So what is the domain of a quadratic function? Can you think of any numbers that cannot be squared? I cannot think of a single number that I'm not allowed to square. Right? So it's all real numbers. Domain is all real numbers. The graph of a quadratic function is called a parabola. You probably knew that. The vertex of a parabola is the highest or lowest point, depending on the geometry of the particular situation. So the highest point vertex would be on a graph that opens down like this. Lowest point would be on a graph that looks like this. Right. And the last little fact here that I want to mention is there's a vertical line that goes right through the vertex. And that thing has a name. Does anybody remember what that's called? Axis of symmetry, or some people call it line of symmetry, right? So I'll call it axis. I think our textbook uses axis. Just want to remind you that the axis of symmetry is more than just a formality. It is a very important part of the graph. Because if you know what line of symmetry is, and you happen to know a point that's to the left of that line, you happen to get a freebie point on the right of the line. So it can help us duplicate points and find more than we thought we knew or something like that, as you'll see later. So these are just some basic facts. You need to memorize them. Domain is all the numbers. Graph's called parabola. What is a vertex? What is an axis of symmetry? All of our problems, we'll try to use interval notation. Remember, for the domain, for example. So we'll be writing this still for all real numbers. Remember that? I'm going to use that in a few weeks. Vertex, we're going to all agree that we're going to call our vertex h comma k. 90% of the textbooks out there use h and k for the vertex coordinates. And axis of symmetry, in this chapter, these are all like opening up, opening down style parabolas. We're not doing those sideways ones right now. You know the sideways parabolas that look like this? We're not doing those right now. So that means all of our axis of symmetry are always vertical, straight up and down. And they will have the equation x equals h. Why are they x equals h? Because, first of all, they're vertical lines, so they should be x equals something. And second, it's passing right through the vertex, which is hk, so it needs to be x equals h. If I ask you to write the equation of a axis of symmetry and you write h, it's not acceptable. It's x equals h. It's a line. It deserves an equation. Okay, so just some little notes there. Let's go to the next page. For graphing parabolas, that's all we're doing today. There are two philosophies on teaching it. Okay, one is what I call method one, and the general strategy is this. You're going to use completing the square to transform from the general form to the standard form. Okay, so this is called the general form. And you're going to try to get it to look like standard form. See? And once it's in standard form, these values A, H, and K have meaning. Okay? The H and the K are the vertex. And the A, of course, is like a vertical stretch or shrink or something. Okay? That's all I'm going to say about method 1. Let's just try it. Our goal is to turn it from general to standard. So I'll give you a second to copy this, and we'll try a problem. So if you haven't taken notes up to here, you want to start because we're going to have 2 examples, and there's going to be a lot of other formulas coming your way, so make sure you jot them down. Okay, so here's our first example. We're going to try to graph this thing using method 1. Right now you can tell it's in general form. A is definitely -3, B is definitely 12, C is -2, but these numbers don't mean much to us. Maybe the A is meaningful. Maybe you know how to use the C value. But I would rather know the vertex. So what I'm going to do is try to convert, this to f of x equals a times x minus h squared plus k. That is much more interesting to me. Okay, so the first thing I'm going to do is factor out the -3 from the first 2 terms. So the first thing you do is you factor out the a value only from the first 2 terms. Just leave this -2 sitting right here. Okay? Then I'm going to take this number right here and divide it by 2 and square it. So divide the linear coefficient by 2 and square the result. Okay, so what is -4 divided by 2 quantity squared? Turns out to be 4. Right. Obviously this will always produce a positive result. You're squaring it. Okay, so you get this 4. Like, what does that mean? What do you do with that? Well, you're going to actually add it to the x squared minus 4x. So the next phase of completing the square is to go ahead and squeeze that brand new 4 in right there next to the linear term. You might say, well, hold on, you can't do that. You can't just throw a 4 into the problem. You're right. We cannot just randomly throw a 4 into the problem unless we keep things balanced. So you need to go ahead and keep things balanced. You just put a brand new 4 into the problem, and it's under the influence of a -3 out here. So you just basically decrease my function by 12. See? 4 times -3. So you're going to have to add a 12 to keep things balanced. And you add that on the outside. So go ahead and add a 12. All right, I'll do it in purple so you know where it came from. So plus 12. Just take 10 seconds, turn to your neighbor, and explain to them how I got the 12 and why I put plus 12 there. So can you do that just real quick? We'll make sure we all know what we're doing. Okay, this is a really important concept, what I just did. Okay, what it did is it just turned my function into this. Now the function is this, if you factor -3 times x minus 2 squared plus 10. We just found the vertex. It's at 210. Okay? It's a very powerful trick. The vertex is at 210. not negative 2, 10. You're supposed to use the opposite of the interior there. So the vertex is at positive 2, positive 10. Great trick. Okay, it's also extremely effective on many other functions. So it's best for, I mean, it's used primarily for quadratics, but the idea of transferring an existing formula into a standard form for graphing sake, that idea is really, really universal. Okay? You might remember some of our earlier work with like the sine wave, right? Let me draw this up for you again. You remember this. We were talking about this recently. I might give you like, 5 minus 2 sine 3x minus pi, and I might ask you to graph it, but if you can put it into sort of a standard look, you can interpret it better, right? We were saying you could write this as negative 2 sine of, then you could factor out that 3 and write x minus pi over 3, right? And then leave the plus 5 at the back here. And what happened is everything has meaning now, right? The 2 is your amplitude. The negative is your reflection. The x minus pi over 3 is your right shift. The plus 5 means go up 5. The 3 there means to vertically collapse, or horizontally collapse it, right? So everything's very meaningful when you put things in a standard form. Okay, so that idea is very universal. We'll use it all year. Okay, in this case, what we found is the most important point, the vertex. So let's go ahead and plot it. Let's go ahead right to up to 3, 4, 5, 6, 7, 8, 9, 10. And that's this point right here. And also you guys know that when the a value is negative like that, the graph is opening down, right? So this negative right here means opens down. And you just got the graph pretty much. Can someone tell us what the 3 means? This 3 right here, what does it mean? It's not an amplitude, but it's a vertical stretch. But how do I use that 3 to sketch the graph in more detail? Does anyone know?
A is equal to 1 over 4. 1 over 4, I think the variable is C, but it can't be C.
Oh, that's, yeah, you're using something from the directrix there. There's like a directrix and focus type thing. Yeah, that's an algebra 2 concept, which we'll hit again later in the book. But the a value is sort of like it's kind of like your slope, right? And so what you do is from your vertex, if you go one space over, the a value tells you how many spaces to go vertically. So this is basically like a rise over run, but it only works for the first unit of run. So what you do is you just go over 1, down 3. Over 1, down 3. That's what the negative 3 means. Okay? So it basically gives you this point right here. Okay, so this was the point 2, 10. And this is the point 3, 7. Okay? And then you also have the axis of symmetry. Right? So where's my axis of symmetry? Now that we have the vertex, it's pretty obvious. Where's my axis of symmetry? X is 2, right? X is 2, so let's draw that in here. And since you have the axis of symmetry, you get 1 point for free. Not only is there a point at 3, 7, but we also have a point on the left side of the axis of symmetry. And where is that at? 1, 7. That point's a freebie. We got it just from symmetry alone. Okay, so how is this method powerful? Well, it's universal. The ideas are universal, that you can turn things into a standard form and every number has meaning. Also, it wasn't that hard to do. Going from the actual equation to the graph is pretty easy. Are there any disadvantages to this method? Okay, you can't solve everything. What do you mean?
Like if you had a coefficient on the x term, it would be a lot harder to solve than 5x, 6x.
Sometimes, yeah. If you have like an a value that is like a fraction, that can be a little awkward. When you try to factor it out, it's a little tricky to factor it out. What else?
But if you have an odd linear coefficient,
Yeah, if you have an odd linear coefficient, then when you're trying to divide by 2 to square it, that can be a little awkward. Sometimes you might have like a 4 here, and it's easy to divide by 2 and square. Sometimes you might have a 9 here, and you try to divide by 2 and square, and you get 81/4. And you have to do it, but it's awkward. What else? What did we not know about this graph yet? Look at the graph. I still have lots of questions about this graph. What do you guys see there that we don't know yet? Yeah, Jack?
X-intercepts?
We don't know the X-intercepts. Exactly. We don't know the X-intercepts. Do we know the Y-intercept?
Not yet.
Not yet. Okay, so we don't get any of that like detail stuff, like intercepts, that sort of thing. All this gives us is the general shape and the location and the direction it's opening. Okay? What's that?
We can get the Y-intercept.
We can get all that stuff. Yeah. There's a formula for everything, right?
Yes.
Now let's say I asked you to find the X-intercepts. How many of you would go consult a formula for that? Anyone? X-intercepts. If I asked you to find the X-intercepts.
Y0.
Okay. Yeah, I was going to ask. And then how many of you would make Y0? Okay, because that's the way to go, right? If I say find the X-intercepts, you want to make Y0. Where's the Y in this problem? Half of X, correct. So you make the left side 0, and I think you're going to find you need the quadratic formula to solve it. Okay? Suppose I say find the Y-intercept. You probably wouldn't want to look for a formula. You just make your X0 and work from there, right? Okay. The second method of graphing parabolas is to just memorize a formula for everything. Okay, this works great for certain people. Not really for me. There's a formula for everything. I'll give you a second to write this down. There's a formula for the axis of symmetry. There's a formula for the vertex. There's a formula for the X-intercepts. There's a formula for the Y-intercepts. The general strategy is memorize a bunch of formulas, plug everything in, and sketch your parabola after you understand it. So here is all your detail. This is most of it. I'll scroll down in about 30 seconds. What goes in these 3 blanks? Does anyone remember? I'll give you a hint. This one is less than, I'll give you a little hint here. This is a less than 0, equals 0, greater than 0. There's something that goes on the left though.
Yeah.
Matt?
Discriminatory.
Okay, it's not called the determinant. It's called the, it starts with D and ends with ent, but it's not determinant. It's discriminant. Yes. There's another thing called the determinant in math. It's a different topic. So it is the discriminant. So if the discriminant is negative, we have no X-intercept. If the discriminant is 0, we have 1 X-intercept. If the discriminant is positive, we have 2 X-intercepts. Maybe you've never really understood why that rule is true. But look up above. The discriminant is just the interior part of the the quadratic formula, right? So if that's a negative number, then you can't square root it. That's why you don't get anything. If that number is 0, then it doesn't matter, and you just get b over 2a, negative b over 2a, which is one answer. And if that number is positive, then you effectively can square root it, and then you'll have a negative b plus a number over 2a and negative b minus over 2a, which is 2 different answers. So it's really not that mysterious, this whole discriminant idea. It's just basically a question of whether or not that radical exists and how many roots it gives. Okay, the y-intercept of a parabola is at 0c, and additional points can be found by plugging in x's. I would add to this last little comment near the vertex. Okay. You're welcome to plug any number you want into the function for x. Okay, plug in 100 if you want, but you're so far away from your vertex that what happens is you get a number, you get like a point that's off the paper. So if you want to have all your graphed points on your graph paper, pick numbers near your vertex. Okay, so put the phones away here. Okay, we're going to do the same problem we just did a minute ago using method 2, where we just kind of use all these formulas and try to just compile a bunch of information. Okay, so let's try it. Same problem, different instructions. So, first thing, I'm just going to let you brainstorm. You can raise your hand if you see something right away that we can do. We're not factoring or anything. We're just trying to use our formulas. What do you notice there, Jack?
Y-intercept is 0, I mean negative 2, 0.
0, negative 2? Yep. Okay, so this right here is probably the only freebie right there. Okay, that means the y-intercept is 0, -2. All right. That's actually kind of interesting because we didn't actually know that when we did method 1. We didn't get that information using method 1. Okay, let's go ahead and plot it. So 0, -2 in red, y-intercept. Got it. We got some formulas we can try, right? Wasn't there a formula like h equals -b over 2a? Let's do that one. H equals -b over 2a. This is to find the axis of symmetry. Take a moment and calculate that. Plug in the b and the a. So x equals h equals -b over 2a. So, okay, what is -b over 2a turn out to be on this problem? -12 over 2 times -3. What does that come out to? 2, right. So looks like x equals 2 is an interesting spot on this graph. So let's draw our axis of symmetry in blue. Label it. Okay, yeah, so we also know one more thing now. The vertex always lives somewhere on that line, right? So we kind of got the ball rolling for the vertex now, don't we? Okay, so let's do the vertex calculations in green. The vertex is supposed to be at hk, which is -b over 2a, comma, f of -b over 2a. We already found that -b over 2a is 2, so we're basically going to find the point 2f of 2. What does it mean, f of 2? What does that mean? Plug in 2 is what it means, right? So let's do that real quick. So f of 2 is -3 times 2 squared plus 12 times 2 minus 2. This comes out to be 10. So we just found the vertex is 2, 10, which we had earlier, but this is a more formulaic approach. Okay, 2, 10. And so now we can plot that. So up to 3, 4, 5, 6, 7, 8, 9, 10. Green vertex. We get a point for free. Also, we get one freebie point using the symmetry argument. So can someone raise their hand who doesn't normally raise their hand and tell me where we have another point? You do not need to do any calculations. We get a freebie point because of this line of symmetry. Yes, ma'am?
Or -2.
Yes, you're right. Right over here, there's a point. What's your justification?
Because it's on the other side of the axis of symmetry.
Correct. So that's the nice thing about the axis of symmetry is you get dual points, right? Okay, so if this is the point 0, -2, then we get 4, -2 for free, right? 3 points isn't bad for a parabola, but we can keep going. Now let's find, we'll use purple, let's find the x-intercepts. X equals -b plus or minus radical. We'll use that. Okay, so x equals -b plus or minus radical. Yes, sing it. Sing like you mean it. Okay. All right, let's simplify that so we can figure out where our x-intercepts are. This is for x-intercepts. So we have -12 plus or minus the square root of 120 over -6. In other words, -12 plus or minus 2 root 30 over -6. And be careful when you simplify these sorts of things. Please pull out a 2 on top or a -2 on top and reduce. Okay, don't get too cancel happy. So why don't we just pull out a -2 on top or something. That'll make this 6 minus or plus root 30 all over -6. And then you can reduce this to 1/3 on the outside. Okay, so this is 6 plus or minus root 30 over 3. Okay, now root 30 doesn't simplify really, so you might want to get out a calculator for this part. But I did that and I basically got 0.174 for one root and 3.826 for the other. And those are your X-intercepts. We could put those on the picture in purple. So right around 0.2-ish, right around 3.8-ish. And there's your graph of the parabola. If you want more detail, go for it. Just don't deviate too far from your axis of symmetry, or you'll find points that are too far down the page. So I don't know, you could try plugging in x equals 1, try plugging in x equals 2. We didn't try that yet. That's to get more points. Okay, I'll show you those decimals again for those who didn't get the chance to copy them. They're at the bottom there. That's the end of the lesson. Okay, I think you should use method 1 for almost everything. The only idea you might want to steal from method 2 is this last part in purple, because that's nice detail, you know? X-intercepts are pretty important. Also the Y-intercept, you can get that before you even start the problem, because you just look at the C value at the beginning. Remember, we got that right away. Okay, on the homework, use method 1 for every problem, except I'd like you to use method 2 for just one problem, okay? Let me say something about matching. You're doing some matching tonight. For matching problems, I found that if you factor the original problem they gave you, if it's factorable, then that is a really quick way to match things up. Also, the Y-intercept is C, so that makes it pretty easy when you're trying to match from the general form.